So we looked at simple data partitioning, and now we're going to look at divide and conquer based partitioning. So the difference is that in simple data partitioning, you take your data and you divide it once, okay, and then you allocate that to your processors. However, in divide and conquer partitioning, you take your data, you divide it, and you don't necessarily stop at that point, right? You might divide again. And the criteria is that if the data is too large, okay, you're going to divide. And then if after that division, you find that the data that each process has is still too large, you're going to keep subdividing. Okay, so we keep taking a problem and dividing it into smaller parts until eventually the parts get to be small enough that they can be solved directly. So sort of algorithmically, you can say that, so we have a problem, and then we look at the size of the problem. And if it's too large, right, then let's say that we divide this into two parts, part 0 and part 1, right? So we're going to solve those parts individually, and then we're going to combine their answers to get the overall answer to the problem, right? And if the problem is small enough, then we're just going to solve the problem directly. And so you can think of this process as happening on a tree. So initially you have a problem, and then you, if it's too large, you subdivide it into smaller problems. Okay, and then and then you look at these smaller problems. If they're still too large, then you're going to subdivide each. Okay, and then you're going to keep subdividing until you end up with these final tasks that you can do individually. So, so just to give a concrete example of this, so if we apply this divide and conquer to our sum of numbers example, right? So where we just want to sum a bunch of numbers, then in the simple data partitioning, we just took this list of numbers and divided them into p pieces, right, with p processors, and then each processor got a piece. So so here instead, we're gonna use the divide and conquer approach, and this is just gonna look at the set of numbers. And if there are too many numbers, right? So as long as you have a list of more than 2 numbers, we're going to keep subdividing that list. Okay, so then you're going to form the first half of the numbers, right? And then the next half of the numbers, you're going to add those individually, and then you add together the result to get the sum of everything. And if there are only 2 numbers or 1 number, right? Then we're going to just add those individually. Okay, so so now we can do this in a parallel fashion also. Okay, so in a parallel fashion, we take the big problem and then we subdivide it. And now the point is that the subdivision process, okay, can be done in parallel, because once you've divided the problem into some number of pieces, right, then these pieces are now independent of each other. They're independent subproblems. And so we can independently look at each subproblem and decide if we need to subdivide that farther, okay, further. So then we have a bunch of subproblems, and in parallel, we're going to look at all of them and see which ones that we need to subdivide some more. So then eventually, after the subdivision process finishes, right, we're going to end up with a bunch of small tasks, and those small tasks can also be done in parallel, okay. And then finally, after we solve the small tasks, we need to combine their answers back together to get the overall answer, right? So the combination phase can also be done in parallel, okay? So the divide and conquer approach naturally lends itself to a parallel formulation. And we can also write everything in terms of a recursive function, which I'll show you later, okay? So there's a nice way to sort of to phrase everything. So the issue here is that since we're doing this divide and conquer, and initially you don't know how many pieces you're going to end up with, right? Then it's kind of hard to write this in an iterative fashion, because usually when you write an iterative program, you need to specify, let's say, how many processors you're going to have and how many pieces of data you're going to work with, right? Well, here, or how many parts of data we're going to work with. Well, here we don't know how many parts there are going to be, right? Because we keep subdividing until we don't know when we stop necessarily. So therefore, it's more tedious to write this in a iterative fashion, and so instead we'll write this in a recursive fashion, as we'll see. And then after you form all of these tasks, you need to assign them to processors. Okay, so the tasks can be represented in this tree structure. And we're going to see how to assign tasks from the tree structure to a bunch of processors. And then we'll also try to reuse processors at different levels of the tree. Okay, so more concretely, so suppose we go back to the problem of adding together numbers. Okay, so we have a list of numbers that we want to add. And so what we're going to do is we're going to have a bunch of processors here. Okay, so we have like P0 and then P1, P2. So we have a bunch of processors. Okay, and then we're going to take our original list of numbers, and then we're going to split. As long as that list is too large, we're going to split the list and give different parts to different processors. Okay, and you see that we have this special way of allocating the processors to the tasks. Okay, so if we have 8 processors, then basically we're going to allocate, so the list is going to start out on the on processor 0, let's say, all right? And then if we subdivide the tasks, we're going to give half the tasks to the first half of the processors. Okay, so that's going to be P0 up to P3. And the other half of the tasks are given to the other half of the processors, P4 up to P7. Okay, and then if we're at a certain point in the computation, so for example, P4's computation, right? And if we need to further subdivide this, then we're again going to split the processors in the subtree in half. Okay, and then so we're going to split the processors P4 up to P7 in half. So we have P4 and P5 on one side, and then P6, P7 on the other side. And then we're going to give the first half of the problem to the first half of the processors, and then the second half to the other processors. Okay, so we always do that. So you at any point in time, you have a problem, and then you have a set of processes that can go ahead and solve this problem. And if you want to subdivide your problem, you're going to give half the problem to half of the processors, and then the other half to the other processors. Okay, so this represents the divide phase of divide and conquer. And eventually, we need to. So then, eventually, we end up with all of these little tasks that are assigned to the processors, and we go ahead and individually do those tasks, right? And we do them in parallel. And notice that the division phase can also be done in parallel, as I was saying, right? Because once you've divided the data between P0 and P4, right, then a P0 needs to further subdivide its data. It doesn't need to interact with P4. It can just do this by itself, right? P0 can act independently of P4, right? And P4 doesn't need to interact with P0. Okay, so therefore these the next layer of division can be happening in parallel. Okay, so all the division is happening in parallel. The solutions to the small problems at the bottom layer are happening in parallel. And then the combination phase, where you combine these answers, okay? So these are also going to happen in parallel. So now when you combine the answers, since you've split the problem onto multiple processors, when you combine, you're going to merge the answers onto one, back onto one processor, okay? And the processor you're going to pick is whoever spawned these two processes, okay? That's the one that's going to continue after you do the merge. So for example, P0 here, he was the one that, if you go back to this, right? So P0 here split into P0 and P1, right? He gave half the tasks to P0, he kept half the tasks, and he gave half to P1. So then later on, when you combine these two guys, right, we're gonna combine back into P0. Okay, and likewise here, P0 spawned P0 and P2. So when you combine, you go back to P0. Okay, so then eventually everything is going to go back to the original processor P0. Okay, so then let's try to write some code for this. So we'll figure out how to do this in a recursive fashion, right? Because as I said, this is easier than writing this in an iterative way. All right, so then the first thing we need to do is that you notice, so here I've just redrawn the picture from the previous slide over here, just so that we can look at it, okay? So, so the first thing is that you notice that these processes, right, are receiving data from other processes, right? Like initially, P4 doesn't have any data itself, okay? And so it's waiting to get data from from somebody, okay? And we have to figure out who that somebody is. So we can see from this picture, it's going to be P0. Okay, but in general, given a processor, how do we know who it's going to receive data from? Okay, so the way that we can know that is actually we can, so if we divide, if we spawn processors in this way, right, where we give half the problem to half the processors, okay, then you can see that the way to figure out, for each processor to figure out who it's going to get data from, is to look at the binary representation of that processor. Okay, and then from that, you can actually figure out who to get data from. So for example, process 0, right? So the binary representation would be all zeros. And this guy, his binary representation would be 100. Okay. And then, for example, process 6 over here, right? His binary representation would be 110. Okay. Now, the way you can figure out who you're going to get data from is you can kind of see this is that if you look at the rightmost set bit, okay, right, that tells you who to get data from. So, for example, if you look at the 6 here, okay, if you look at the rightmost set bit, that is this bit corresponding to 2 over here, right? Right, this bit over here, okay. Now, if you turn that bit off, okay, what do you get? Okay, if you turn it off, you get 100. Okay, and that's actually who 6 should be getting its data from. Okay, it's process 100, which is 4. Okay, so if you find the rightmost set bit in a process and you turn that off, then that's who you get your data from. Okay, likewise, if you look at 4 over here, if you find the rightmost set bit, right, well, that's just the first one, right? If you turn that off, you get 0. Okay, and that's who you get your data from. Okay, now maybe another example, right? So if you have 100 here, right? So here you have process 101, process 5, right? So the rightmost bit is this one. If you turn it off, you get 4, which is exactly who 5 gets its data from. Okay, so therefore, the way that you figure out who to get data from is you turn off the rightmost bit. Okay, now that is what's being done over here. Okay, so this receive from is so this is again kind of like MPI pseudocode. Okay, so for the MPI pseudocode, when you receive, you need to know who you receive from, and this is computing who you receive from. So this command over here, okay, this kind of cryptic command, okay, this is actually turning off the rightmost bit. Okay, so what it's actually doing is it's taking my rank, right? It's taking the rank of the process in binary, and then it's doing a binary AND, a bitwise AND with my rank minus 1. Okay, so just to give an example how this works, right? So our goal here is to turn off the rightmost bit, set bit of my rank. Okay, so for example, if my rank is something like 1011, okay, then my rank minus 1 is going to be 1010, right? If I do the AND over here, right, then you see that this is going to be 1010. And so that basically here I've turned off the rightmost bit. Okay, another example, if you had a different number here, so he had 1010 here, right? If you subtract 1, you're going to get, what do we get? We get 1001, right? If you do the bitwise AND, right, you see that you're going to end up with 1000. Okay, so again, you've turned off the rightmost set bit. Okay, so that's what this receive from, that's how that works. Okay, so next, so now we figured out how to who to receive from, but what about how much data we want to receive? Okay, so now in terms of how much data you want to receive, right? So for example, 4 over here, right? If you have, let's say, 8 values, okay? So for simplicity, let's first assume that we're going to have the same number of processors as numbers, okay? And both, let's say, are a power of 2. So in that case, process 4 is going to receive 4 pieces of data from P0, because we have 8 pieces of data overall, right? So it's going to be a 4 over here, right? And then, so let me try to clear this up a bit. Yeah, and then for example, this 6 over here, right? This is going to receive 2 pieces of data from P4. Okay, so we need to be able to figure out these quantities, like the 4 and the 2 and so on. And the way you do that is we're going to use this thing receive count over here. So now you see that the way you can figure out how much data you need to receive, okay, is that you can look for the you can find the rightmost set bit, okay. So we're not trying to turn off the rightmost set bit anymore. We're just trying to find the rightmost set bit, and that will tell you how much data to receive. Okay, so for example, the rightmost set bit of P4 is going to be this one thing over here, and that corresponds to 4. Okay, so that tells you that P4 needs to get 4 pieces of data. Likewise, you have this P6 over here, right? Its rightmost set bit is going to be the 2-bit, right? The bit corresponding to 2, and so he gets 2 pieces of data. Okay, now as another example, so let's see, so this guy is 100, right? This guy is 101, right? So the rightmost set bit is the 1 bit, right? And so that tells you that P5 is going to get 1 piece of data from P4. Okay. All right. So then this is so then we need to find the rightmost set bit, and again we're going to use this sort of bit trick to find the rightmost set bit. And then, so I'll just give you an example how this works. So my rank, so suppose my rank here is something like 4, okay? So then what this is doing is it's taking the AND of this with the negative of my rank. Okay, so the way that we can write the negative, so we're going to use the 2's complement. So what that means is, so the way to compute the 2's complement is we're going to take the number my rank. You're first of all going to flip all the bits. Okay, so if you flip all the bits, you get a 1011. Okay, and then you add 1 to that. Okay, and then if you do that, let me try to give myself a bit more space over here. So so we're going to flip the bits, right? So we're just computing the 2's complement, if you remember how that works. So so that is flipping the bits. It's adding 1 to it, and then what does this give us? It gives us 1100. Okay, and then if you take the bitwise AND of this 1100 with the with my rank, right, then you see that you get exactly this bit over here, right, and this is indeed the rightmost set bit. Okay, so that's what, yeah. So we have these 2 sort of mysterious looking commands, but all they're doing is they're finding the rightmost set bit, right, and then they're also taking that out. Taking out that bit, right? And this tells us who to receive from and how much to receive. Okay, so now knowing all, so now after we've computed all that, so let me clean this up a bit. Okay. All right, so we don't need this anymore. So then now this this part over here, right? So then this is saying that well, initially all the data is on the is on process P0, right? So the guy with rank 0. So then he's going to call this function over here. This is a recursive function. This function is the add function, right? And he's going to say that okay, I want to add these numbers. There are n numbers here, and my rank is 0. Okay. Now so that and this is because P0 initially had all the numbers. But if you're not P0, then initially you don't have any numbers. So the first thing you need to do is to get some numbers, okay? And the way you do that is you're gonna get these numbers, and you're gonna receive this number of values, right? So where we computed this over here, and you get it from this guy, okay? All right, so then after you get these numbers, now you can go ahead and call this this add function to add them up, okay? And then after you add them up, right? You're going to get a single result, right? And then you're going to send this back to whoever you got the numbers from, right? Like for example, P3 over here, right? Well, he got some values from P2. So after he computes these values, right, he's going to send his answer back to P2. Okay, and likewise, P2 got the numbers from P0, so he'll send it back. Okay, that's what the final send does. Okay, and lastly, we have this recursive add function. Right, so the recursive add function is going to say that I'm getting count numbers, right? And I actually I want to keep subdividing this until I'm down to 2 numbers. So if I have too many numbers right now, I'm going to split this in half, right? I'm going to send half of these numbers, okay, to somebody, okay? Now, who do I figure out who to send to? Okay, so that it's actually going to be it's my rank plus the number of values I have. Okay, so for example here, right, P4. Okay, so his rank is 4, and he got 4 values, so he wants to send out 2 values, and so he's going to send this to rank plus S, which is 4 plus 2, which is 6. Okay, so P4 sends to P6. Okay, and for the remaining numbers, for the remaining half of the numbers, he's going to add them himself. Okay, and then after that, he's going to so he over here he sent half the numbers to somebody, to rank plus S, and here he's going to get back the sum of those numbers from rank plus S. Okay, and then he computes the sum of both numbers, right? And then that's his output. Okay, and otherwise, if he's just got 2 numbers or 1 number, then he just returns the direct sum of those numbers. Okay, so that is how we can implement this divide and conquer approach in MPI. Okay, so now in terms of the oh, right, so then here we have the same number of processes as numbers, right? So of course, in general, you don't have to do that. You could have fewer processes than numbers. Okay, so you could have 1,000,000 numbers, but you just want to add them on like 10 processors. Okay, so then here what you can do is you can keep subdividing until the list of processors that that is in your subtree, right? So whatever that list of processors is, those are the guys who you can use to help you solve your subproblem. Okay, but if you're only down to a single processor in your subtree, then there's nobody else left to help you. So in that case, you got to go solve the problem yourself. Okay, so therefore the way to express that is we're going to keep subdividing the problem until we're down to like 1 processor. Okay, and then you just have to solve the problem yourself. And so basically, this is gonna the net effect of this is going to be that this is going to assign n divided by p numbers to each of the processors. Okay, so let's look at the efficiency of this algorithm. So assume for simplicity, n and p are both powers of 2. Okay, so then for the first part, for the division part, okay, so we're going to keep subdividing until we're down to 1 processor. So therefore, this is going to take log p steps, right? Because we're sort of going to double the number of processors we use in each step. Okay. Right. So the computation time for this step is going to be log p. That's the number of steps. The amount of communication that's happening, right? So initially, all the data was on a single processor, and he sent half to somebody, right? And then whoever got that half of data, he had to. So he processor 0, right, sent half his data to somebody, and then he sent a quarter of his remaining data to somebody else. Right, and then he sent an eighth of it to a third person, to a third process, and so on. Right. So yeah. So if you look at it over here, right. So initially he sent 4 pieces of data to P4, right, and then he sent 2 pieces of data to P2, and then 1 piece of data to P1. Okay. So in general, P0 had to keep doing this, right, until he was down to n divided by p pieces of data. Once he got to that point, then that data would have been sent to just 1 process, okay? And that 1 process, and at that point, in P0's subtree, there was only 1 processor left. So after sending that amount of data, then P0 has to just take whatever data is left and solve that problem himself, because there are no more processes to help him. Okay, so if you add this up, this is going to add up to a geometric series. And the sum of all of this stuff is just going to come out to something like this. Okay, so all right, so that's good. Okay, so yeah, so that's the total time for that. Okay, so next we're going to look at so that was for the division part of the algorithm, right, where you keep subdividing. Okay, so the next part is to actually do the computation. So so for the computation, each node ended up with n over p pieces of data. Okay, n over p numbers, basically. Okay, so you just add those up, and that takes you like n divided by p time, or maybe that thing -1. And then you have to go back and you have to combine these numbers. Okay, so that so the combination part is also going to be log p steps. However, when you combine, the messages are always going to have size 1, right? Because you're just sending your sum to your parent process. Okay, so instead of sending multiple numbers, you send the sum, and so each message has size 1. So therefore, the computation time for that is going to be log p, because there are log p layers, and the communication time in total is, well, you do this log p times, and each time you send 1 piece of data. So yeah. All right, so then you add all that stuff up, and then it's going to come out to some expression like this. Okay, so it's something like order n plus order log p plus order n divided by p. Right, so here is the time to add. Here's the time for communication. Right, this is like how many layers of communication you have to do, and then this is the total amount of data that you had to send. Okay, so unfortunately here, again, we don't really get any speed up, because the sequential running time would also be order n, and then our parallel running time is order n, and so, you know, because you had to send the data out at the beginning, we don't get speed up. Okay, now, even though we don't get speed up in this case, that doesn't mean that parallel divide and conquer is not useful. So, for example, if we apply this to our previous numerical integration example, okay, so here's a nice instance where we can apply this. So, yeah, so the reason you might want to do divide and conquer data partitioning as opposed to simple data partitioning is that you might have a function where you need to subdivide certain subproblems more than other parts of the subproblem. Okay, so right, so an example of that would be so if you have a function which changes a lot in some area and changes very little in some other area, okay, then you would want to have a finer subdivision in the places where it changes a lot versus a coarser subdivision where it changes a little. Okay, so this is kind of being illustrated over here, where you can kind of see that there's less error on this part. Sorry, there's less error on the shaded part than on the white part over here. Okay, or we can do a more sort of dramatic example where suppose you have something like this. Okay, suppose you have a function which kind of looks like this. All right, so then if you were to just subdivide the pieces, let me sort of draw this so that they look like they're the same size as each other. So if you subdivide the pieces so that they're all equal to each other, okay, so that they're all, so it's like delta here and then delta here, okay? Then since we're using a trapezoidal approximation for the area, right, then you see that we're going to have a pretty large error over here, okay, just because the function is changing a lot. So it doesn't actually look like a trapezoid. Whereas over here, right, you're going to have a very small error, okay? You can hardly see it. Okay, so then what that suggests is that on the left-hand side, you actually don't want to use a very coarse subdivision. You actually maybe want to subdivide this guy a bit more. Okay, oops. So my function is was looking like that. Right. Let's just redraw everything. Okay, so so we had a function that was looking like that. Okay, so now if you just so you might actually want to subdivide the left-hand side some more. Okay, so if you do that, then you see that we're going to substantially reduce the amount of error, right? Then the error is just going to be these two slivers up there. Okay, so yeah, so this shows that in certain parts, right, you want to use a smaller subdivision. Okay, and parallel divide and conquer lets you do that, because you can say that given a problem, right, I can keep subdividing until I'm happy with whatever size I have. So when you do this, you can call this adaptive quadrature, okay, because it adapts to the error that's that you encounter, okay, and so this can help you increase your accuracy. So we're going to take a region that a processor is assigned some region to integrate, okay, and it's going to take that region and then keep subdividing it and then allocating different parts to its sort of helper processes until the error gets small enough. Okay, so then we might end up subdividing some regions a lot. Yeah, so it adapts to the shape of the curve, and then we can represent this computation using a tree. Okay. Now this time it might not be a complete binary tree, right? Because so for example, you know, if you start with the initial problem and then you subdivide it, right? So then you get two subproblems, right? So maybe this guy wants to subdivide some more, and this guy also wants to subdivide, right? So now here you might have this problem is still you still need to subdivide here, okay? And then maybe this one you need to go farther, okay? Oops. Okay, but maybe for this problem you're already happy with the accuracy. Okay, so you can just stop at that point, right? And maybe this guy you're happy with, and then this guy you want to subdivide some more, and then you're happy. So you see that you can still represent the overall set of subproblems as a tree, except for you don't have to have a complete binary tree, because you don't have to subdivide to the same degree everywhere. Okay, yeah, and so now because it's not a complete binary tree, it becomes a bit more challenging to allocate processors to this tree. Okay, so later on we're going to talk about how to allocate. We're going to talk about sort of the scheduling problem and the processor allocation problem. Okay, in another lecture. Okay, yeah, so just pictorially, you know, this is what it would look like. Okay, so if you had a big problem like this, right, then you see that this would cause substantial error over here. Okay, and then so this is too much, so therefore we're going to divide this into two subproblems. Okay, and then that's going to reduce the error, right? So now we're not going to have C as being the error. We're just going to have these you know, these slivers up here as being the error. Okay. So so basically, so this is saying that, well, what criteria can you use to decide when to stop subdividing? Okay, the criteria that you can use is that you can form this this triangle C over here. Okay, so the triangle C is taken by if I have a let's see. So if I have this region over here, right, then what I'm going to do is I'm going to take the midpoint of this region, right, and I'm going to form this triangle. Okay, if this triangle has a large area, then this is saying that I'm going to get a large error if I just use this this trapezoidal region as is. Okay, if I just use that trapezoid, I'm going to get at least this triangle C worth of error. So then if the C is too large, right, then I'm going to decide to subdivide. Okay, I'm going to divide this in half. Okay, and then once I divide it in half, then in both A and B, I'm going to run the same test. Okay, so for example, in B over here, right, I'm going to try to see if B is good enough. And the way I figure that out is I divide this in half, right? I form this triangle over here, and then I look at whether I'm happy with the size of this triangle. Okay, so I set some threshold for that. Okay, so that is how we do divide and conquer partitioning. And so that covers the two types of partitioning, data partitioning we're going to talk about. So next, we're going to move on to algorithmic partitioning. Okay, so algorithmic partitioning, remember, is that we're going to not break the data into different parts, but we're going to break an algorithm into different parts. Okay, and then each part of the algorithm is going to sort of take turns processing the data. And so a good example of this would be a pipeline computation. So here, suppose you have a computation and you manage to break it into like 6 parts, and there could be even more parts out here. Okay, and so what's going to happen is you're going to have a piece of data, right? So the data is going to come in, and it's going to be processed by every one of these parts. Okay, right? So we need to do so each of these parts does some operation on the data, and the overall algorithm we need to do all these parts. So the data gets passed through these parts one by one. Right, and they have to be executed in this order. The steps have to be executed in the order shown, and then yeah, and then we can assign the. So if we have a bunch of steps and a bunch of processors, we can have some sort of mapping between the steps and the processors. So in this example, we're showing sort of each processor is just doing one step. But we could actually have, for example, more steps than we have processors. Okay, so in that case, we can actually break up some of those steps, and we can put multiple steps onto one processor. Right. So here, we have 4 steps, and then we can run all 4 on one processor, right? And the next 4 on the next processor, and so on. Okay, so an example of this would be, suppose you want to compute a power series. Okay, so suppose you want to compute the value of sine. So usually the way you do that is through a power series, right? And so now you can represent this power series as, well, first of all, we can write a sequential way to implement this power series. Okay, so we have a loop over here, right? So the loop is just going to compute these individual terms, and then it's going to add them together. Okay, to form this, the sum is basically going to be the value of sine theta. Okay, so so the sum is, so the first term in the sum is just going to be the theta, right? So that's the first term in the power series. And then after that, we're going to form these subsequent terms. And the way you do that is, you notice that, you know, for each of these terms, you could either just compute the term by itself. Okay, so for example, this term over here, right? You can just take theta to the 5th power and divide by 5 factorial. Okay, but then that would take you quite a number of operations. And so you can observe that it's actually faster that, suppose you've already computed the previous term, okay? Then you can compute the next term just by taking the previous term, and then if you multiply this by theta squared, and then you divide by 5 and then by 4, right? Then you can get the next term, this term over here. And so that's what we're going to do, okay? We're going to take the previous term, we're going to multiply by theta squared and then divide by some stuff, and then we're going to get the next term. And then you add the next term into your sum, okay? Okay, and then if you unfold the loop, you see that you're going to get exactly the same computation as the power series. Okay, so now the way that you can do this in a pipeline is that, yeah, so then you can use a bunch of different processors, and each processor is responsible for adding, so each processor is given a single task, and that single task is to add one more term to the power series. Okay, so for example, the P1 guy, right, he's going to add this term to the power series. Okay, the P2 guy, right, he's going to add this term, okay, and so on. And so if you have a bunch of processes, they're going to end up adding a bunch of terms, and then the output of the final process is going to be the value of sine theta. Okay, so actually we'll do this in more detail in a later slide. Okay, but before that, I want to talk about different types of pipelines that we can have. Okay, so yeah, so the process is to take a problem and divide it into a series of sequential tasks, and then run these tasks in a pipeline fashion. Right? And then this can actually increase our speed, as we'll see. So, but in order for this to happen, we actually have to be able to run the pipeline. Okay, so if you want to execute a pipeline computation, you need to have certain properties. Okay, so for example, one situation where you can run a pipeline is if you have more than one instance of the problem to solve. Okay, if you just have one instance of the problem to solve, then maybe you cannot execute this in a pipeline. But if you have multiple instances, you can run the multiple instances concurrently through the pipeline. Okay, another situation where you can use a pipeline is if you have a series of data items to be processed. Okay, and then each of those data items requires multiple operations, right? So requires going through the pipeline, and then you have multiple data items. Then you can also set up a pipeline. And the third situation is where if you you have a bunch of processes and they're running concurrently, but the information that the next process needs, okay, so the processes are in a chain, and the information the next process needs, right, can be acquired from the previous process before the previous process has finished all its computations. Okay, so the previous process is doing some computations, but maybe like halfway through, it can already send some data to the next process so that the next process can get started. Okay, if you have this type of situation, you can also get a pipeline. Okay, so we can look at this more pictorially to make things more clear. So here, So we're going to say that we have these three types of pipelines, 1, 2, and 3. Okay, so the first type is where you have more than one instance of the problem to solve. And so illustration of that would be like this. Okay, so you have a pipeline computation like this with multiple stages, right? And every instance of the problem needs to go through all of these stages. Okay, and so we have time going in the horizontal direction, and so this is a p-stage pipeline with p processors, and suppose you have m instances of the problem. Okay, so the first instance comes at the first time step. It's processed by the first stage of the pipeline, and then it moves on to the next stage of the pipeline. But then at the same time, you can do the first stage of the second instance. Okay, and then at the third time step, you can do the third stage of the first instance, the second stage of the second instance, and the first stage of the third instance. Okay, and then you can just keep doing this until each of the instances has passed through all p stages of the pipeline. Okay, and you can see that the total execution time, if you have m different instances, right? Well, it's going to take p minus 1 time for the first instance to get to the final process, right? And then after that, you see that at the final process, for each additional time step, you're going to get another instance being processed by the final process. Okay, so then since you only have m instances, then after m additional time steps, you finished all the instances. Okay, so the total execution time is going to be p minus 1 time to get the final process started, right? And then m more time to finish everything. So altogether, it's going to be this. So all right, so for the type 2 type pipeline, we can again use some sort of this type of representation to understand the situation. So we're going to call this a space-time diagram. Okay. So what is going to happen is so again you have a bunch of stages of the pipeline, right? So you have p stages of a pipeline, and then you have now a single data item needs to go through multiple stages of the pipeline. Okay. And then you have multiple data items. Okay, so D0 is the first data item, right? It's going to go through all of these pipelines. And then D1 is the next data item. It's also going to go through all the pipelines. And if you have n data items and you have a p-stage pipeline, then again, the total execution time is going to be p minus 1 steps for the first process to, for the final process to get started, and then n more steps to finish everything. Okay, so the total execution time is m plus p minus 1. Okay, and the final type of pipeline is where you have a process that even after it even before it finishes, it can already pass some data on to the next process. Okay, so an example of this would be that so you have a process P0 over here, right? So overall, the data needs to traverse through all of these stages of the pipeline. Okay, so there are like 6 stages overall here, right? And then so the data is being processed by P0, right? And it takes this much time for P0 to finish. However, even after P0 has partially processed the data, it can already send some data over to P1. Okay, and once P1 gets that data, it can start its computation. Okay, and overall, P1 needs to compute for this amount of time. But even after computing for a short while, P1 can now already pass some data over to P2. Okay, so now P2 can start, right, and it can do the same thing and pass to P3, and so on. Okay, so that's one example where so here all the processes we assume that they have the same execution time. You can do the same thing if you even if the processes don't have the same execution time. Okay, you can still have a situation where you've done part of your computation and then you send whatever data you have over to the next process so that he can also start, right? Instead of having him just wait for everything, right? I mean, the alternative to running this in a pipeline would be that if you do all of P0, right? So you could, so let's see. So I'm going to switch to blue here, right? So if you don't do this in a pipeline fashion, then you would have to wait for P0 to completely finish before you before you give all the data to P1. Okay, so then P1 would only be able to start after P0 finishes, right? And then maybe P2 here can only start after P1 finishes, okay, if you don't use a pipeline. So you can see that if you don't use a pipeline, the overall running time is going to be much larger than if you do use a pipeline. Okay, let's do a more detailed example of the first two types of pipelines. Okay, so yeah, so we're gonna assume P processors, P tasks, so P stages, right? So then each stage we're gonna assume is gonna do some sort of computation. We're gonna call this a basic unit of computation. Okay, and so we're gonna assume that let's see, yeah, so we're gonna assume that all cycles of all tasks take about the same amount of time. So yeah, so the basic computation takes T cycle amount of time. Okay, so then the let's see, the parallel execution time. All right, so this yeah, this NC is the number of cycles that we're gonna do. Okay, NC is an let's go back to red. I think red is actually easier to see. So oops. Yeah, all right. So then NC here is the number of cycles we're gonna do, and then TC is the amount of time for one cycle. So therefore, the total execution time is going to be T cycle times NC, the number of cycles. And the time for one cycle is, so that's going to have two parts, the computational part and the communication part. Okay, so it's going to be the sum of these two things. And then the number of cycles is going to be, so you can get that from the previous diagrams. Okay, so for example, for the type 1 pipeline, we had the number of cycles was m plus p minus 1, right? Because you know, it took again, it took p minus 1 cycles for the final process to start, and then we had m problem instances. So yeah, so that's the total number of cycles, and so the execution time would just be you know, this NC here times T computation plus T communication. And then for type 2, the number of cycles was the number of data items plus p minus 1. Okay, so more concretely, so let's look at an instance of the type 1 pipeline. Okay, so here we can say that suppose we have a pipeline to compute the power series, the sine function. Okay, so the pipeline is, again, different stages of the pipeline are going to add different terms. Okay, so the stage adds this term, P2 adds this term, and so on. Okay, so you can write this out. So we're going to use some sort of MPI pseudocode over here. So what we're going to say is, well, the first process, right, he is the guy that starts with the value theta. Okay, so he's just going to, so if I'm the first process, I'm just going to send my value over to P1. Okay, and otherwise, all the other processes are going to first receive a value of theta, right? And then they're going to receive a value of R, and then let's see, what is, okay, so R is going to be the partial sum. Oh no, I'm sorry. R is the previous term. Okay, so R is like the so these things are the R. Okay, so there are these terms that we compute. Okay, and the sum is going to be these partial sums that we compute. Okay, and the theta is just this value over here. So so each process is going to receive a theta value. He's going to receive the previous term that was computed, right? And he's going to receive the previous sum that was computed. Okay. And then he's going to take the previous term, and so for example, this let's see, well, this is still R here. Let's write it this way. Okay, so for example, P2 is going to receive this theta cubed divided by 3 factorial term, the r from P1, right? He's going to do this type of thing to it, right? So that's going to get the his r term, right? The theta to the 5th power. And then he's going to add that into the sum that he also got from P1, okay? And then if he's not the final process, he's going to send this to the next process. And then you see that the final process will end up with the output. Okay, so then this is a pipeline, and the way to bound the running time of the pipeline is that, so here you see that the basic cycle so what is the basic computation that these processes do? Okay, the basic computation is that every process is going to do this part of the computation, right? So then we just have to figure out how much time this is going to take. So this is going to be our basic cycle here, right? And the amount of time it's going to take is just we count the computation time. Let's see. I'm not sure how I'm getting this 4 over here. Okay. So, anyways, so the computation is just how many arithmetic operations we do. Okay. So somehow like I put a number 4 here. I'm not sure what I was counting exactly, but anyways, it's some sort of constant, okay? 4, 6, 8, something like that. And then you have the communication time. So the communication is being done over here, right? So this is communication, and then this is also communication, right? And the communication is, each time we're sending like 3 pieces of data, right? 3 pieces of data, and then you do that twice, okay? So this is the communication time, okay? And the time for one cycle is the sum of these two things, right? And then the total number of cycles is going to be so now if you just have a single instance of the problem, okay? So suppose you're just trying to compute. Let's try to clear this up. Suppose you're trying to compute just a sine of one value, okay? Sine of one theta value, okay? Then you have exactly p stages of this pipeline, right? So therefore, the number of cycles, if you have a single instance, is going to be p, and so the total running time is going to be like this. Okay, it's something like p times a constant, right? This constant over here. Okay. However, this is not efficient because even if you compute the sine value sequentially, right? So eventually you're going to get p terms over here. So if you do the sequential computation, that would also take you order p time. So if you just do one instance of the sine computation using a pipeline, you don't get any improvement in efficiency. However, if you have multiple values of theta, okay, suppose you have m values of theta, okay, then now we can go back to the previous analysis, and now the total number of cycles to solve all m instances is just m plus p minus 1. And so if you plug that into the formula, right, so then we have the t cycle time times the number of instances, okay? And now the averaged amount of time per instance, okay, is going to be this execution time divided by m, right, which is going to be this thing over here, okay? And so basically this is saying that for large values of m, okay, then if you're computing many sines of many different value, then basically this whole thing is just going to come out to a constant, okay? So if you compute many sines, then it basically just takes you a constant amount of time to compute each sine value. And there, of course, that is a speed up, right? Because if you compute this sequentially, it's going to take you order p time. Whereas if you compute this per instance, okay, whereas if you compute this with a pipeline, it takes you constant time per instance. So here you get a perfect speed up. You get an order p speed up. Okay, another example of this would be, so now here we have an example of the type 2 pipeline where you process multiple pieces of data, okay, in the pipeline. And so here, suppose we look at insertion sort, okay? So insertion sort, what we're gonna have is, we're gonna be sorting, let's say, n numbers, okay? And then we're gonna use n processors to do this. And we're trying to sort the numbers, let's say, in decreasing order. So what's going to happen is each processor is going to, whenever it receives a value, so it's currently storing some value, okay? And it receives a new value, and if the new value is larger, it keeps it. It keeps a new value, okay? And it sends the previous value that it was storing to the next process. Right? Otherwise, if the received value is smaller, it'll just pass the value it received on to the next process. Okay, so here's an example of this, right? So suppose you're trying to sort 5 numbers over here, right? So we're going to use 5 processes, and suppose the numbers are in this order over here. So 5 is first going to be sent to process process P0, right? And then P0 doesn't have any numbers, so it stores 5. And then you send 2 to process P0, right? And then 2 is less than 5. So P0 just passes 2 on to the next process, right? And then the next process is going to store 2. And then also 1, you send 1 to P0, right? But P0 is going to pass 1 onwards, and so on. And so, and then you keep doing this. And for example, at some point you see that 3 is going to get passed from P0 to P1, right? Now, P1 used to be storing 2, and when it gets the 3, it's going to keep the 3. Okay, and when it gets the 4, it's going to keep the 4 and then send the 3 to the next guy. Okay, so you see that if you keep doing this, right, then eventually after all the stages of the pipeline, right, so there we have let's say n numbers here, and then we have n processes. So the total number of stages is going to be n plus n minus 1, so 2n minus 1. After that number of time steps, we're going to sort all the values. Okay, so then, yeah, and the basic cycle is going to consist of, we're going to store a value, and then we're going to compare the value with our current value, and maybe pass on the value. Okay, yeah, and so this is the code for doing that, right? You receive a number, you compare it to your current number, and then maybe you send that number onwards, okay? You send either your current number or you send the you send either your previous number or you send the new number onwards. Okay, and so so this is our basic cycle, and yeah, so the process I is going to pass n minus I minus 1 numbers onto process I plus 1. Okay, because you have that many processors to the right of process I. So then it's going to execute the basic cycle that number of times. Okay, so all right, so it's going to basically process I is going to execute the basic cycle m minus I times. Okay, so therefore the sequential running time of this is that process 1 is going to execute the basic cycle m minus 1 times. Right, sorry, process 0 is going to execute this m minus 1 times. Process 1 is going to execute this m minus 2 times, and so on. So, so altogether, you're going to execute the basic cycle order n squared number of times in a sequential setting. In a parallel setting, so the basic cycle is going to have a receive, a send, and then this comparison operation. Okay, so the computation time is going to be, let's say, 3 steps, right? The communication time is each time you just send 1 piece of data. So the communication time for each cycle is going to be just this thing over here. Sorry, you receive a piece of data and you send it. So it's going to be 2 times this thing. And so the time for 1 cycle is just the sum of these. And the total number of cycles is going to be n plus p minus 1, where p is equal to n. So it's going to be 2n minus 1. And so the total computation time is going to be the cycle time times the number of cycles. So it's going to be something linear in n. Okay, so the parallel execution time is linear in n, and then the sequential time is going to be order n squared. And so you get a factor n speed up, right? So you get a linear speed up in this case. Okay, all right, and the final example is going to be an example of the third type of pipeline, where you can start the next stage before the current stage finishes, okay? And the example we're going to have is So suppose you're trying to solve linear equations where the equations are written in this upper triangular form. Okay, so and this is used in things like Gaussian elimination. Now I'm going to show you more concretely what I mean by this. But basically, first, what's going to happen is that each process is going to do this. Okay, so each process pi is going to receive a partial solution from the previous solution from the previous process. Okay, and it's going to take that partial solution and pass it on to the next process. Okay, pi plus 1. Okay, and then it's also going to use that partial solution to sort of update its computation. Right? Pi is going to use that partial solution to update its computation until eventually pi finishes its computation. Okay, and then pi is going to send the solution that it produced over to pi plus 1. Okay, so initially it's just passing these partial solutions that it received from the previous guy over to pi plus 1. Okay, but eventually pi itself is going to produce some sort of solution, which it's also going to send to pi plus 1. Okay, and here, in fact, we're going to have the different processes are going to compute for different amounts of time. Okay, all right, so now more concretely, we're going to solve these upper triangular equations, these systems of equations. And so, so that means that we have a set of equations, and they're upper triangular because all of the coefficients below this diagonal are going to be 0. So initially, you're going to have a process P0, and he's going to have this equation, A00 times X0 equals B0. Okay, so then he can directly just solve for X0. Right? X0 equals B0 divided by A00. All right, so then once he knows X0, then he can send X0 over to B1. Okay, and then B1 can use that information to compute X1. Right. However, B1 is also going to send this information over to B2 to P2. Okay, so in fact, as soon as P1 gets the value of X0 from P0, he's going to pass it on to P2. Okay, and then after that, P1 is going to compute the value of X1. And once he gets the value of X1, he's also going to pass that on to P2. Okay. Now P2, once it gets X0, he's going to pass it on to P3. And then eventually he's going to get the value of X1, which he's also going to pass on to P3. Okay. And furthermore, he's going to compute the value of X2, right? So once P2 gets the values of the X0 and X1, then he can compute X2. And then once he's got X2, he's going to pass that on to P3. Okay. Right, and so these are the computations that each process does, right? So the first process just computes B0 divided by this stuff, right, by A00, right? And then X1 is going to compute, P1 is going to get the value of X0, and then he can use that to compute X1, right? And then P2 is going to get the values of X0 and X1, and he can compute X2, and so on. Okay, so if you look at the pipeline, then this is like a representation of the pipeline. Okay, so we're going to have, if we have n unknowns, we have n equations, and we're also going to use n processes. Okay, so if we write this out, then what we're going to do is that okay, so this is the code for pi where I is larger than 0. Okay, so so every process besides P0 is first of all going to so he's going to have the sum over here. Okay, so the sum is just going to be this part over here, right? Okay, so the goal of the process of pi is to compute this entire sum, and once he's got the entire sum, then he can compute, he can subtract it from bi and then divide by aii and then get xi. Okay, but to compute the sum, right, he needs to get all of these other xi terms, or sorry, xj terms, where j is less than I. Right? Yeah, so he's so pi is waiting to get all of these xj terms. Okay, so each time he gets one of these xj terms, right, then he's actually going to pass this on to the next process, because the next process also needs the xj term. right? So yeah, so pi gets it from gets xj from pi minus 1. He gives it to pi plus 1, and then he's gonna add one more term into his sum. Okay, as soon as he gets xj, right, then he can add that into his sum. Okay, so so eventually he's gonna wait for to get I minus 1 pieces of data from pi minus 1. Okay, and he's also gonna pass that stuff on to I plus 1, and then he's gonna have the sum value computed, and once he's got the sum, then he can compute xi. Okay, and once he's got xi, he's also going to send xi over to pi plus 1. Okay, so altogether, he's going to send I pieces of data over to pi plus 1. Right, he's going to send all this stuff. Right, so here you have I minus 1 pieces of data, and then one last value for xi. Right, and then process 0, he's just going to send his he can compute x0 directly, and he's going to send that over to process 1. Okay, so then we have n stages of our pipeline, and in terms of execution time, now if you look at the total amount of work that needs to be done, right? So you see that process I needs to basically do I amount of computation, right? And so for the sequential execution time, process 1, or sorry, rather process 0 is going to do 1 unit of computation. Process 1 is going to do 2 units, and so on. So altogether, they're going to do order n squared amount of computation to compute all the xi values, all the x values. For the parallel computation, process I is going to perform, you can see that process I is going to do I multiplications and additions, and then also, so he's going to do basically, process I is going to do like I operations over here, right? These multiplications and additions, and then he's going to do like a subtraction and a division. Okay, so process I is going to perform basically I amount of computation. Okay, and also process I is going to do 1 receive and 1 send before the next process can start, right? Because you can't start your computation until you get your first value. Okay, so now in order to figure out when when let's say process I plus 1 can start, we see that process I has got to receive all these I values. Let's see. So process I has to receive a single value and send a single value before process I plus 1 can start, right? So as soon as process I receives a value and then sends it on to I plus 1, then I plus 1 can start. Okay, so basically, if you so to receive a value and to send a value, this is going to take this much time, right? So this basically means that the second process can start after this amount of time. The third process needs to start this amount of time plus when P2 started, right? So P2 is going to start at this time. So P3 is going to start at this one times, 2 times this time, okay? And then P4 is going to start at 3 times this time, right? Because P4 can only start after P3 starts, and P3 starts at 2 times this time. Okay, so therefore, in general, you're going to have that P of m minus 1 is going to start at m minus 1 times this time. Okay, and then also process m minus 1 is going to perform m minus 1 arithmetic operations, right? And so his computation is something like this, okay? And then process m minus 1 is gonna let's see. So he's gonna do he's gonna do m minus 1 receives, okay? And then actually he just does 1 send, okay? So there should just be like a 1 send over here, okay? But to do the m minus 1 receives is basically gonna take him this much amount of time. Okay, so the because process m minus 1 keeps receiving these xi values from the lower processes, right, for I from 1 to m minus 1, okay? For I from what, 0 to m minus 2, I guess. Okay, and then so process m minus 1 is going to spend basically linear time on the receives. He's going to spend linear time on the computations, right? And he is only going to start at this time, right? Because we said that p of m minus 1 can only start after that amount of time, and this is when he gets his first value. Okay, and after he receives his first value, right, then he's going to do some additional receives and some computation. And if you add all this together, you get that the total computation time for p m minus 1 is going to be linear. Okay, and so if you compare this with the sequential execution time was quadratic, right, was n squared. Okay, and now the pipeline running time is linear. And so therefore you get a linear speed up. Okay, you get order n speed up using n processors. Okay, so that's all we have to say about the this lecture. So next time we're going to look at this current lecture focuses on designing algorithms in the distributed memory setting. And so next time we're going to look at parallelizing algorithms in the shared memory setting.